Yeah, U-substitution is more or less the chain rule in reverse, right? So if you have the chain rule for derivatives, then, and this is an antiderivative, right?
Right.
The opposite of the derivative, you can do the chain rule process in reverse. So if you can find some inner function that is the derivative of something on the outside, or derivative of it is on the outside, I should say, then you can see that this is the result of the chain rule, and you can reverse that process.
Sure.
But integrals are kind of like that, in that you have a derivative which has a pretty straightforward process for calculating whatever the derivative is, and the integrals are a little bit more, I don't know, I guess I could say right-brained. You kind of have to try stuff and see what fits.
Right.
But yeah, U-substitution in this case will definitely work. What we want to do is say U equals something on the inside. Hopefully something that'll make this a simpler integral.
Right.
Right. So maybe if it were U instead of x plus 1, that would be nice. So that's what I would try first, to say U equals x plus 1. But we don't only substitute out the x with U, we want to substitute the dx also. So we take the derivative of this in order to find dx. So what is the derivative?
So just to hopefully correctly reiterate what you're saying that we introduce a variable u and set that equal to the inner function?
Yeah, something on the inside like x plus 1 to make it an easier integral.
Okay. And you take the derivative of u, is that what you're saying?
Mm-hmm.
Right. So I just supposed up until now that if we had this variable u, then taking the derivative of that would sort of be something along the lines of this notation here, whereas you're using d. Is that the same?
So let's just do it the way you're thinking first.
Sure.
All right, du dx. What is the result?
Okay. Well, that would just the derivative of x plus 1 would in fact be 1.
Yeah, this is 1. Now let's multiply both sides by dx.
Is there any reason as to why you're choosing to do so?
The reason is because I want dx in terms of du.
Okay. You want dx in terms of du.
Mm-hmm. So then I get du equals dx.
Sure.
Which means I can just directly substitute that in as it is. Which means this integral becomes, instead of x plus 1, we have u squared. And instead of dx, we have du, because they're equal. Okay?
Right. Okay. Sure.
And this is an integral that hopefully you know what the rule that we should apply here is.
So you want to use the reverse power rule in order to attain the...
Yeah.
And that would be it?
That would be it. That would be it until you have it in terms of u, and then you would put the original x version back in.
So if we could continue with this here, we would just find that this would be u to the 3 over 3, and after this we simply substitute, I'm assuming what u was, x plus 1, in this particular, so we have x plus 1 to the 3rd raised to 3. Is that what you're saying here?
Yep. And then, of course, to make a general solution for all possible antiderivatives, you put the plus c at the end. Yeah.
So would you, Trevor, right? Would you perhaps mind looking at another example if I were to put it on the whiteboard, just so we can find, maybe just so we can apply the same reasoning in a different context?
So I think that would be a great idea because, to be honest, this example doesn't really give very good flavor for how the U-substitution really works out most of the time.
Sure.
This was kind of like an easy one. So yeah, let's take a look at another one and see how that goes.
Okay. And I think you're absolutely right, because I think we lost in this problem. I think we've lost the presence of a number here, maybe, or something here, or a term.
Mm-hmm.
And I think if maybe in something like this, if I were to, so if I had, if I were told to compute something like the cosine of 6x dx, I think maybe this would do some justice.
Yeah, that's not really going to be a good example either.
Really?
It's going to be the same thing. Well, there will be a number. So I guess this is not too bad. Sure, let's do this one.
Sure. So I guess off the basis of what you said in the last example, you wanted to somehow replace both the dx and the inner function with u.
Yeah, we can see this and say, we know if we were to take cosine of u du, if we had something like that, we could do that, right? We know a rule.
Right.
So that's what we would want to go for.
Okay. Okay, that makes sense. So u would equal to 6x, and then I think you also added that we would also want to take the derivative of u, or du with respect to x, which would equal 6. And I think you also said that, or is this dx? But okay.
Yeah.
Okay. And I think you said you wanted to also have dx in terms of du. So
that's ultimately why we're doing this derivative. Yeah, that's what it's for.
That's why we're doing what exactly?
This derivative.
I see. That's why we're doing the whole derivative thing, just so we can express it in terms of du.
Mm-hmm.
Even this part here?
That part gets you this done.
Okay.
But we need this in terms of du. So that's what the derivative is for.
So taking the derivative of u is essentially just a, it is sort of, it's because we want to express dx in terms of du.
Right.
Okay. So then we get, so if we were to multiply, so we'd get 6 dx is what we'd get here.
Mm-hmm.
And then I guess what you said before was we can rewrite as being having maybe as having u here with dx, which is 6 dx, or cosine u rather, I think. Does that?
Mm-hmm. Yeah, that's right. We want this in terms of u, though. So let's rearrange this so we can get that.
Okay.
No. No.
Really?
Dx was right.
Dx was right?
Yeah. That's not how we want it. It's not done, but that's mathematically correct to do this. Okay. But we want it in terms of u. Okay, so what we need to do is we need to solve for dx here.
Solve for dx.
Yeah, dx equals 1/6 du. So this is what goes here. So this becomes cosine of u times 1/6 du.
So you wanted to sort of maintain dx here, but you wanted it in terms of du. So you solved for dx in terms of du. So whether or not you put dx or 1/6 du there doesn't make too much of a difference, since they're both equal to the same thing.
Mm-hmm. Yeah, well, dx and du are not the same thing. That's what this equation proves. They're not the same thing.
But there is an equal sign.
Well, it's 1/6 du. Okay, this 1/6 is the thing that makes them different.
Okay.
Okay, so you can't just take this dx and swap out a du. You got to swap out this.
Right. Okay.
They were equal before in this example.
Sure.
So this is a special case, but in this case, they're not. So you need this 1/6 in here.
Okay, so seems like we solved for dx in terms of du and then put du there. And now I suppose we would, so we still have, so we have a function multiplied by another function here. And I don't think with integrals there is something resembling the power rule, fortunately. Or not the power rule, but the product rule.
Product rule. There is a reverse product rule. That's not what we want to do here, though.
Is it not?
No. What we want to do here is recognize that 1/6 is a constant coefficient.
You want to pull it out?
Okay. Yeah, you can just pull it out just like derivatives.
Okay. And I suppose we would just be looking for the antiderivative of cosine.
That's what we've reduced this down to.
Okay. So I guess that would have to just be, so I know that the derivative of sine is cosine, so I suppose the antiderivative of cosine would be sine. So I think 1 over sine of u du.
Good.
And I suppose now we would do the sine of what u was, which was 6x, I believe. But is it wrong to use x?
Du anymore. The du is gone.
Really?
Because you evaluated the integral, so du is gone.
Interesting. So I guess we're writing it in terms of x now.
Yeah, you don't need the dx either, right?
Oh, right. Okay.
It's this plus c.
Okay. Sure. Plus c. Is that it?
Yeah, that's good. That's it.
Okay. All right. Well, I'll try to take away from this what I can, and hopefully apply this later on.
You want one more example, perhaps?
Sure, please. Although I'm not too sure about solving it, but yeah, I mean, do you have an example off the top of your head, maybe?
You betcha.
Okay.
Let's do this one. X e to the x squared dx.
Okay. So immediately, I mean, I find the composite function or the inner function being x squared. And I think somewhere vaguely I remember, and I'm not too sure, I didn't look too much into it, but what they said was that you only take u as being something which has, in other words, the derivative of your u should be somewhere in the integral or in the integral question. So if I were to take
you would like that. That would definitely make it much better. Otherwise, doing the U-substitution might make your integral worse.
Right.
So,
absolutely.
Yeah.
So I suppose it's safe to take u to be x squared.
That's a good choice.
And of course, to then remove dx, I would take the derivative of u, and of course take the derivative of x squared as well. since we want to maintain equivalence on both sides, which would be 2x. And so it seems like we've done that much. And now let's see here. So I think I can, let's see.
Yeah, get all of your x stuff on one side and all your u stuff on the other side.
Sure. So
That's
solve for, so I guess I could multiply by dx.
Mm-hmm. This is the thing you always do at this stage for these U-substitution. Yep.
Dx. And this is, of course, in attempts to have dx in terms of du.
Mm-hmm.
Okay. And then divide by d. Well,
you're undoing what you just did. Yeah.
Right, exactly. I think I should divide by 2x.
That's better. Yeah.
So then I have my dx in terms of du.
Yeah, and now you see how you have x on both sides?
Yeah, I do see that, yeah.
Normally that would be a bit of a problem because you would be putting x back into this when we're trying to get rid of all the x stuff. But this 2x here and this x here are going to go together very nicely, as you will see, hopefully in a moment. So go ahead and start doing the substitution.
Okay, sure. So I suppose now I could have x and then e to u, really. And of course, I would be in terms of, I would have du over 2x, because this whole thing is in terms of u, as we mentioned. And it seems as though since the integral of x alone, I think that went to 1. So is it safe to rewrite x as 1?
Well, x over x is what you have.
Oh,
right?
so that would cancel out, is what you're saying.
Yeah, that's what's happening.
I see. And then we're just left with this particular component here.
So you got the 2 here, but yeah.
Oh, right, of course, yes. And so really this comes down to finding the integral of, I suppose it would be e to the u multiplied by 2 to the negative first.
And du, yeah.
Oh, of course, yeah. And du, and then of course pulling out the constant.
Yep, constant coefficient comes right out.
Okay. And then recognizing that the since the derivative of e to the x, or in this case e to the u, I suppose, is e to the u, then the reverse is also true in terms of the antiderivative.
Yep.
So really, we're left with e to the x squared over 2. And
then cherry on top.
That's really it.
Yep.
Oh, plus c, right? Of course.
That's plus cherry on top. You got to put that for every antiderivative. Yep.
Is there
unless you only need a antiderivative? There are cases where if you only need a antiderivative, you don't need every antiderivative. You don't need the plus c. But in this case, we're looking for a general solution, right? All solutions to this integral. And so you put a plus c here to say there's a family of antiderivatives, and they all differ by a constant. So putting that plus c there gives you an expression for representing the whole family of antiderivatives. Does that make sense?
To some extent, I suppose. To some extent.
Well, yeah. So if I have some function that has some that's like this,
sure.
I take the antiderivative of it. This may not be the scale, but it might be some group function like this, where this function represents the slopes of this function. Let me actually make a better representation of that. Right, if this is our function f, then our integral or antiderivative of f is going to be the one that has these as its slopes.
Right.
So it would be decreasing, decreasing, and then it'll hit 0, become increasing for a second, and then become 0 again, and become decreasing for a while, but very slowly, shallowly, and then it's going to start over here, it's going to become 0, and then start becoming very positive again, right? It'll be something like this, as a graph whose derivative would be this.
Sure.
Right? But the same thing would apply to this graph up here. Or this one.
Right.
Okay? They all have the same slopes. They just differ by how high up or down they are.
Mm-hmm.
If you take the derivative of this, they would all equal this same thing. So this is why if you go from here to here, right, the inverse function, if you will, it's not one-to-one. So this gives you multiple possibilities.
Right.
But the only difference between them is how high up or down they are. And that's what this plus c does, is it shifts the graph up or down.
So you're saying please go on.
So by putting this plus c, you can say this expression represents every possible answer you could get out of this. Right? If I put a plus 0, that might be this one. You know,
right.
If I put plus 1, that would shift it up by 1, so it would be this one up here. If I made it minus 1, it would shift it down by 1 to put it to this one, or whatever shift you want. Any vertical shift will give you another function whose derivative is this. So the antiderivative of this could be any one of those.
So so there would be an infinite number of constants which could represent the place of c. So this would be like a general sort of a...
The general theorem of antiderivatives is that if you have whatever antiderivative you get when you calculate the antiderivative, any other antiderivative that's the same as that, except maybe by a constant difference, plus or minus some constant, is also an antiderivative.
Sure. I think that makes a lot of sense. If you don't mind me asking, how would this process, what we've just outlined in terms of U-substitution, how would this process differ in the context of, let's say, a definite integration?
It would be the same, because you would be finding an antiderivative. The difference is that once you get that antiderivative, you don't have to say plus c, because what you're doing is you're evaluating the antiderivative at two different points, the end points of the integral, right?
Right.
And then you take the difference between them. And so whatever antiderivative you use, plus c is going to cancel out because you're taking the difference between the two.
Absolutely. So is it safe to say
that's
that...
That's why in that case, you don't need every antiderivative. You just need a antiderivative.
Sure. So if I was given a problem which very much resembled the question that you've given on whiteboard 2 for a particular interval, is it safe to say that...
1 to 2.
Right.
Yeah.
Is it safe to say that they would be the exact same solution with the exception of the c?
No.
Okay.
What we would do is we would say ex, and we would say, okay, that works out to be 1/2 e to the x squared as plus c, right?
Right.
You could put the plus c in there. It wouldn't be wrong. You could put it there. But then you would evaluate these from 1 to 2 like this, right?
Right.
which means you take 1/2 e to the 2 squared, right, the upper integral, plus c, minus the other one,
Right.
1 squared, plus c. And the rule is you have to use the same antiderivative for both of these, right? Which means that c is the same in both cases.
Right.
And if that's the case, then they're just going to cancel out. You're going to get 1/2 over c, 1/2 e to the 4 plus c minus 1/2 e squared minus c, because you distribute the minus sign to both of these terms, right?
Sure.
So c minus c, that cancels out, and you're just left with this, which is the same thing that you would have gotten if you hadn't put the plus c there in the first place. So when taking a definite integral, the U-substitution process is exactly the same. You get exactly the same result. And the plus c you could put there, but once you evaluate the definite integral, it goes away. And so in this case of calculating a definite integral, the plus c is not necessary.
Sure. And is it expected for us, knowing sort of the knowing that the c will sort of
Yeah, you were kind of expected to know that in a definite integral, you just need this part. You don't need the plus c, because the plus c is just going to cancel out anyway.
Okay, I understand. That sounds reasonable, because of course, since our c's will cancel out in every case, since we are of course subtracting.
Yeah, it doesn't matter what integral you're doing, the plus c is going to cancel out if it's a definite integral.
Sure.
It's only there if you're looking for a general solution for all antiderivatives.
Absolutely. Well, I think I'll just I think I'll reflect over this and try to solidify sort of what you illuminated here, and and hopefully I can take it forward.
Yeah, so too. But yeah, it's good questions.
Thank you. Thank you.
Keep up the good work, okay?
Awesome.
And feel free to start a new session if you get stuck again, okay?
Okay, absolutely. Well, thank you for your time, Trevor. I hope you have a wonderful night.
Yeah, thank you. You as well.
Okay, bye.